Beneath our feet lies a world few truly understand, where unimaginable forces and temperatures shape the very fabric of our planet. From the fragile crust to the scorching inner core, each layer plays a crucial role in Earth's existence. But what mysteries lie within these layers? What secrets are hidden in the depths, shaping everything from the continents we stand on to the magnetic field that shields us? As we peel back the layers, a story of immense power and ancient history begins to unfold, one that will change the way you see the Earth forever. The crust is the outermost layer of the Earth, forming the solid surface that we live on. It is the thinnest of the Earth's layers, varying in thickness from about 5 kilometers under the oceans to up to 70 kilometers under continental mountain ranges. Despite its relatively thin profile, the crust is incredibly important as it contains all the natural resources necessary for life, such as soil, water, and minerals. The Earth's crust is divided into two main types: the oceanic crust and the continental crust. The oceanic crust is denser and thinner, primarily composed of basalt, a dark, fine-grained volcanic rock. This crust forms the ocean floor and is constantly being renewed at mid-ocean ridges where tectonic plates pull apart and magma rises to create new crust. The continental crust, on the other hand, is thicker and less dense, composed mainly of granite and other light-colored rocks. This crust forms the continents and is much older and more complex in structure compared to oceanic crust. The crust is not a continuous layer but is broken into large pieces called tectonic plates. These plates float on the semi-fluid asthenosphere beneath them and are constantly in motion, leading to geological activities such as earthquakes, volcanic eruptions, and the formation of mountain ranges. Within the crust, there is a rich variety of rocks and minerals that have formed over millions of years through processes like cooling, erosion, and sedimentation. This diversity is crucial for human civilization, providing resources such as metals, fossil fuels, and building materials. The lithosphere is the rigid, outermost shell of the Earth, encompassing the crust and the uppermost part of the mantle. It plays a crucial role in the planet's geological structure and dynamics. The lithosphere is typically about 100 kilometers thick, but can vary depending on whether it's beneath the oceans or continents. Beneath the oceanic crust, it is thinner, while beneath the continental crust, it is thicker and extends deeper into the Earth. The lithosphere is divided into large, rigid pieces known as tectonic plates. These plates are constantly in motion, driven by forces from the underlying asthenosphere, a more ductile layer that behaves like a slowly flowing fluid. The interactions between these tectonic plates at their boundaries are responsible for much of the Earth's seismic and volcanic activity. For instance, where plates converge, they can form mountain ranges or cause subduction, where one plate is forced beneath another, leading to earthquakes and volcanic eruptions. Conversely, where plates diverge, mid-ocean ridges and rift valleys can form, creating new crust. The lithosphere's rigidity contrasts with the more fluid layers beneath it. This rigidity is crucial for the functioning of plate tectonics, as it allows the lithosphere to act as a cohesive shell that can fracture and move, leading to the dynamic surface processes we observe on Earth. Another critical aspect of the lithosphere is its role in the rock cycle. It is the source of all the planet's solid surface rocks and minerals. The lithosphere's rocks are constantly being recycled through processes such as erosion, sedimentation, and volcanic activity, contributing to the formation of new rocks and landforms. The asthenosphere is a semi-fluid layer of the Earth's mantle that lies just below the lithosphere, typically extending from about 100 kilometers to 200 kilometers beneath the Earth's surface. Unlike the rigid lithosphere, the asthenosphere is partially molten and behaves plastically, meaning it can flow slowly over geological timescales. This unique characteristic is crucial for the movement of tectonic plates, as the asthenosphere provides a lubricating layer over which the rigid lithospheric plates can move. The asthenosphere is composed primarily of peridotite, a dense, ultramafic rock, which is partially melted at this depth due to high temperatures and pressures. This partial melting makes the asthenosphere ductile and capable of flowing, albeit very slowly, which is essential for the process of mantle convection. Mantle convection is the slow, churning movement of the Earth's mantle caused by heat transfer from the deeper interior of the Earth to the surface. This convection drives the movement of tectonic plates, leading to phenomena such as continental drift, seafloor spreading, and the recycling of oceanic crust back into the mantle at subduction zones. The asthenosphere's viscosity is low enough to allow the lithosphere to move over it, but it is still strong enough to transmit seismic waves. This dual nature is key to understanding many geological processes. For example, when tectonic plates move, the interaction between the lithosphere and the asthenosphere can result in earthquakes, volcanic activity, and the formation of mountain ranges. The upper mantle is a significant layer of the Earth, lying directly beneath the crust and extending down to about 660 kilometers below the Earth's surface. It is a part of the Earth's mantle, which is composed primarily of silicate minerals, rich in iron and magnesium. The upper mantle, along with the crust, forms the lithosphere, and below the lithosphere lies the more ductile asthenosphere. The upper mantle plays a crucial role in Earth's geology because it is the source of magma that leads to volcanic activity. This magma is generated due to the high temperatures and pressures that cause rocks in the upper mantle to partially melt. The molten rock can rise through the crust to form volcanoes, or it can crystallize within the crust to form igneous rocks. The upper mantle's composition is dominated by peridotite, a dense, high-pressure rock that is primarily composed of the minerals olivine and pyroxene. In addition to its role in volcanic activity, the upper mantle is also crucial for the process of mantle convection, which is the slow, churning movement of the Earth's mantle caused by heat escaping from the Earth's interior. This convection drives the movement of tectonic plates, leading to continental drift, earthquakes, and the creation of new oceanic crust at mid-ocean ridges. The upper mantle is divided into two distinct zones: the lithospheric mantle, which is rigid and forms part of the lithosphere, and the asthenospheric mantle, which is partially molten and flows slowly. The boundary between these two zones is not sharp, but rather a gradual transition where the rigidity decreases with depth. The lower mantle is the largest layer of the Earth's interior, extending from about 660 kilometers to 2,900 kilometers below the Earth's surface. It lies beneath the upper mantle and above the Earth's outer core. The lower mantle is composed primarily of silicate minerals, including bridgemanite and ferropericlase, which are stable under the extreme pressures and temperatures found at these depths. One of the defining characteristics of the lower mantle is its rigidity compared to the upper mantle. Despite the intense heat, ranging from 1,600 to 2,800 degrees Celsius, the lower mantle remains solid due to the immense pressures that reach up to 1.4 million times the atmospheric pressure at the Earth's surface. These conditions prevent the rock from melting, making the lower mantle much less fluid than the asthenosphere above it. This rigidity means that, although the lower mantle is capable of very slow, solid-state flow, it does not flow as readily as the upper mantle. The lower mantle plays a crucial role in the process of mantle convection, which is the slow, heat-driven movement of material within the mantle. This process is vital for the transfer of heat from the Earth's core to the surface and drives the movement of tectonic plates. Convection in the lower mantle is slower and more sluggish than in the upper mantle due to its greater density and viscosity. However, this movement is essential for the recycling of oceanic crust back into the mantle at subduction zones and for the upwelling of hot mantle plumes, which can lead to volcanic hotspots. The lower mantle's composition and behavior also have significant implications for our understanding of seismic activity. Seismic waves travel faster through the lower mantle than through the upper mantle, providing important clues about the Earth's internal structure. The outer core is a crucial layer of the Earth, located beneath the lower mantle and extending from about 2,900 kilometers to 5,150 kilometers below the Earth's surface. Unlike the solid lower mantle and inner core, the outer core is in a liquid state, composed mainly of iron and nickel, with minor amounts of lighter elements such as sulfur and oxygen. This molten state is due to the extremely high temperatures ranging from about 4,000 to 6,000 degrees Celsius, which are sufficient to melt iron and nickel at these depths. The outer core plays a vital role in generating the Earth's magnetic field. This process, known as the geodynamo, occurs because the liquid iron and nickel in the outer core are in constant motion due to convection currents driven by heat escaping from the inner core. As these molten metals move, they generate electric currents, which in turn produce magnetic fields. The combined effect of these magnetic fields creates the Earth's global magnetic field, which extends far into space and protects the planet from harmful solar radiation and cosmic rays. The flow of the outer core's liquid metal is also influenced by the Earth's rotation, leading to complex movements and the creation of the geomagnetic field's intricate structure. This magnetic field is not static. It undergoes changes over time, including periodic reversals where the magnetic north and south poles switch places. These reversals are recorded in the geological record and are believed to be driven by the dynamic processes within the outer core. The outer core's liquid state also has a significant impact on seismic activity. Seismic waves generated by earthquakes behave differently when they pass through the outer core. Specifically, S waves, shear waves, cannot travel through the liquid outer core, while P waves, compressional waves, slow down and refract. This behavior helps scientists determine the size, composition, and state of the outer core.